Physics has a problem, and that problem is, why is there stuff in the universe? A simple answer to this would be that the Big Bang created all of the stuff in the universe, from me to you to all of the galaxies we see in the Hubble Deep Field and everything else beyond. But there's a problem with quantum mechanics. See, quantum mechanics doesn't really agree with this interpretation. And to understand why that is, we need to talk about something called CPT symmetry. And what this stands for is 3 different properties that if you link them together, they make a symmetry in physics. The C just stands for charge, so it's meaning that a positive charge should obey the laws of physics just as a negative charge should. The P stands for parity, which means that a particle and its mirror image should also behave through the laws of physics. In this case, they'll move off the screen. And the T stands for time, or time reversal, meaning that if you flip time around, physics should still behave as you would expect. So this creates a symmetry which is very important in physics. But it also creates a problem. You see, if there was a CPT symmetry, we have a universe that is filled with nothing. And the reason that's the case is because the Big Bang would produce an equal number of positive and negative particles, the particle and its antiparticle. And these particles, with CPT symmetry in place, would all find their antipair, collide with each other, and produce a bit of light. So would go from a universe filled with stuff to a universe devoid of anything. So this is, of course, a big problem. It doesn't match what we see in reality. So how can we resolve this problem? Well, there are a few theories of how you could break CPT symmetry. One of them is to do with neutrinos, but the one we'll talk about in this video is to do with neutrons. We all know and love neutrons as those subatomic particles that sit at the nucleus beside protons. And bartenders all hate them because they never pay for their drinks. But the neutron isn't a fundamental particle. It's made up of 3 smaller particles, being quarks, an up quark and 2 down quarks. Although the neutron doesn't have a charge, these quarks do have charges. It has a positive charge for the up quark and 2 negative charges for the down quark. And summing these charges together leads to a 0 charge, or a neutral neutron. But there might be something called an electric dipole in a neutron. You see, these charges from the quarks don't necessarily all cancel out at the same place. So you could have one side of the neutron being slightly more positively charged than the other side. In this case, the side with the up quark might be a little bit more positive than the side with the down quarks. And if this were the case, it would introduce a way to break CPT symmetry. So this is a big goal for quantum physics, is to try and determine what the electric dipole of a neutron is. And it's a pretty complicated thing to do. But if they do find an electric dipole for a neutron, we'd solve this problem. We'd go from a universe where we predict nothing to exist to the universe we have today. And what we're going to be looking at is a paper that was released recently, which talks about an experiment which has nailed down the electric dipole of a neutron to the highest precision so far. And this paper comes from Sussex University, led by Chris Abel, but it has an enormous collaboration behind it, which have done fantastic work. So how did they measure the electric dipole of a neutron? Well, they did it through a process known as Lamar precession. Now this is a process where if you take a particle like a neutron, which has a property known as spin, and put it in a magnetic field, and if you slightly misalign the spin axis of the particle with the magnetic field lines, you'll have the particle precessing on its spin axis around the magnetic field lines. And the frequency of this precession is determined by both the magnetic dipole and the electric dipole of the particle. So to put it in a mathematical sense, this is the equation that they were dealing with. It's a bit complicated, so let's break it down. The first term, pi over h bar, is just a constant, so we don't need to worry about that. The second term, mu n, is the magnetic dipole of the neutron, so we don't need to worry about that either, it's just a constant. The third term is a magnetic field that they put through the experiment, so this is also a controlled variable. And the last term here is an electric field that they put through the experiment, which again is a controlled variable. This term that we skipped over, dn, is the electric dipole of the neutron. That's the thing that they want to find out, and to find that out they need to measure this thing over here, Fn, which is the Lamar frequency of the neutron in a magnetic field environment. So how do you measure this Fn? Well, you need a very complicated setup, and this is a schematic of their setup. It's pretty complicated, so let's just go through it in steps. First thing to point out is this big cylinder in the middle. That thing there is where all of the experiment takes place. So it's shielded from the environment with lots of very impressive materials to stop magnetic fields getting in, electric fields getting in, and environmental fluctuations from messing it up. For a neutron, the journey starts down here. It passes through this 5 Tesla magnet, and it then goes through this spin flipper, so they can align the spins of all of the neutrons that come through into this experiment. They'll then find their way to the switch, which then directs them up into the testing chamber. Inside this testing chamber, the neutrons are ultra-cooled, so they're very still and not jiggling around too much. And it's at a density of about 2 neutrons per cubic centimeter or something like that. So it's very sparsely populated. Alongside the neutrons, they inject something else. They inject mercury atoms, which have been also aligned through a similar process. And they use these mercury atoms for calibration, as we'll look at later. And over here we have an ultraviolet light source, which is used to adjust the spin of the neutrons. Above the neutron chamber there is this electrode, which they use to again test to try and find what the electric dipole might be. And once they've done all of their testing inside of this chamber, the neutrons get funneled out down that tube again towards this detector where they can analyze the spin of the neutrons and detect where they end up. So that's how the experiment works. They send the neutrons in, they put them in this chamber where they fire lasers at them to adjust the spin so that they'll then Lamar precess, and then they do this a few times and change the electric field inside the chamber. Then they read out the number of neutrons that have a certain spin up and the number that have a spin down. And this difference between the two is known as the asymmetry. And this asymmetry is crucial to the measurement. So what they find is something like this, where this is just some mock data. The y-axis is the asymmetry, which is the ratio of one spin to another spin. And the x-axis is the thing that they're trying to actually measure and understand, the Lamar frequency. They measure in 4 distinct places along this curve here to make sure that they can fit the curve as well as possible. So you can see the data points just kind of sitting in these 4 distinct places. And they did something very interesting. They had 2 independent groups that did the analysis, and both groups got data that wasn't quite correct. There was some blind offset to the data to make sure that they couldn't actually find the correct answer. So these 2 groups had their own information and had to work out a way to best process that data. And once they'd both done that, they swapped the data to see if their results agreed, and once that was all done, they applied both methods to the real unbiased data. This method is known as blinding, and it's a very useful way to make sure that your science isn't being biased by human thinking, or to make sure that it is actually reproducible, if you reproduce it while you're doing the experiment. So they go through all of this complicated analysis to make sure that they're right, and they end up with a plot like this. So what we have here is a very complicated graph with lots of different colors. The blue sections are when the electrode at the top of the chamber was negatively charged, black is when it had no charge, and red is when there was a positive charge. And through the different testing scenarios, they got all of these data points. Now, to correct for the local distortions in the magnetic field, they used the mercury atoms I talked about earlier. They were kind of a backup detector. So if they divide out by the trends that the mercury atoms also saw, they get the plot on the bottom, which shows there really isn't much going on through changing the electric field. So if this isn't really changing that much, then that probably means that the electric dipole is very small for a neutron. So they went through all the calculations and all the analysis, and they found that the electric dipole is this: 0.0 plus or minus kind of 1.3 times 10 to the minus 26. And if we put that into decimal places instead of scientific units, we end up with something like this. So it's an incredibly precise measurement, and this measurement is said to have thrown out numerous theoretical models of how we could violate CPT symmetry. So it's an incredibly important experiment, and the group hasn't stopped here. They're working to further push down the limits, because to make sure that we know what we're doing, we need to either confirm a theory or prove that it is a good prediction for what happens in nature, or rule it out by finding evidence to the contrary. So they can't really stop until they roll out every single model which predicts CPT violation through a neutron dipole. So this was a pretty complicated paper, for me at least, since it's not my field, but it was super cool to read about it and the state of quantum mechanics and the research that's going on. I've left links to the paper in the description below, along with a link to the press release. If you want to talk about this paper or any other research that's going on, feel free to leave a comment below. But for now, thanks for watching.